This work introduces a defense approach against adversarial attack. The experiments are conducted on speaker verification tasks. Our approach could be also extended for other similar tasks. Here we introduce the common structure of a speaker verification system. The inputs are human voice associated with a claim to his identity. The output is a accept-reject decision. Inside the system, there is a speaker embedding extractor that converts the voice into a fixed-dimensional vector that captures human voice biometric identity. Along with the extractor, there is a dictionary that fetches the enrolled speaker vector of the person claimed to be. If the two vectors match, for example, their cosine similarity score reaches a predefined threshold, the claim will be accepted. For simplicity, let X be the input voice, theta be the embedding extractor, S be the speaker claimed to be, and the capital S be the similarity score. We can find that the similarity score, the capital S, is a function with two inputs, X and the small s. If we ignore the small s, we can see that for each input voice X, we have a corresponding score, capital S. For adversarial attack, it modifies the input voice X with a very subtle adaptation such that it can be hardly perceived by human, either by eyes or ears. But the similarity score of the SV system changes a lot. This reflects the vulnerability of most existing SV systems, including but not limited to A vector, X vector, R vector, end-to-end, and UCAP. Some have been reported in recent papers, some have been found in our experiments. Attack algorithms have been proposed a lot, and some have been introduced in our paper. On the right-hand side, we provide two speech voices with one of the two has been modified to successfully attack the X vector system. Defense approaches still need more investigation. The existing methods can be divided into two categories, either modifying the input X or modifying the model theta. For the former, the defender assumes the precipitation is added into the input X or is some feature representations. It should be noisy-like and can be easily removed from the input X. Motivated by this, spatial smoothing, downsampling, deep filtering have been proposed. For the latter, the idea is to use a data-driven model to memorize all possible attack perturbations as it can. With adversarial training, the SV model can be less sensitive to subtle perturbations. Bad attack detection perturbations can be identified by a well-trained classifier, especially those it has seen in the training phase. For both categories, there are some assumptions on the perturbation patterns, but from the perspective of attackers, altering the perturbation patterns in the feature level is not a big issue. This makes the attack detection a non-trivial task. Here are some observations from two recent papers, which show their proposed attack detectors failed to detect unseen attacks. On the left-hand side, above table evaluates the detect performance in terms of detection accuracy. The higher the better, and we can find out when it is trained on BIM perturbated data, it failed to detect GSMA attack. In the table below, the evaluation metric is equal error rate. The lower the better. On the right-hand side, the situation is similar. With the attacks have been known in training, detection is satisfying, but it is just not on unseen attacks. Our idea is to motivate from the score function. we detect attacks from the similarity score. Here we visualize the score functions of two models, R vector and X vector. The main observations are that, first, score functions of different systems are not the same. Second, under attack, the score functions of different SV systems have a significant gap, even though both systems may be fooled by the attacker. Here is the structure of our proposed SV system that incorporates an attack detector inside. It contains two SV models that output a pair of scores. The primary score model is a well-known X vector. It has some pre-trained model released and public available. The mirror one is R vector with time reverse voice signals as the inputs. The aim is to make it unique and enlarge its difference to common designs. The reversing also keeps all speaker-related information, and it does not affect SV performance. The attack detector is a one-class classifier, which is trained on normal samples. It does not require any adversarial samples for training, which simplified its deployment process. Basically, all attacks are unseen to our proposed system. The final acceptance needs to satisfy two conditions. First, the score from the primary model should reach its threshold. Second, the two scores should pass through the consistency check from the attack detector. Here we visualize the scatter plot of score pairs produced by the two models. The x-axis and the y-axis represent the score functions of scores from the primary and the mirror. Each dot represents a score pair. If a score pair lies in the bottom left corner, it means both the two models have low confidence in accepting the speaker claim. And the top right corner means high confidence. For genuine target trios, red dots, which is the voice matches the claim speaker, this should be around the top right corner. And for the genuine non-target trios, the blue dots, they should lie in the bottom left corner. This behavior shows the score consistency between the two models when there is no attack. But under adversarial impersonation attack, the non-target trios tend to move to the top right corner as the attack algorithm evolves, which represents the green dots, the purple, and the yellow. However, the non-targets actually get more susceptible to the targets in the 2D space, as shown in the figure. This reflects the score inconsistency under adversarial attacks. The primary model is more vulnerable under such attacks compared to the mirror one. We then use a red eclipse to include all the genuine target trios, which is the decision boundary of the attack detector. This includes almost all the attack trios, with the threshold of the primary model X vector, which is a gray vertical line. The final trio acceptance region is defined. Another insight is that we reduce the acceptance region to defend adversarial impersonation attack. For normal SV systems, the attacker only needs to push the non-target trio scores across the system threshold. But now they also need to move them into an eclipse. That is, they also need to guarantee the score consistency between the two unknown models. And this could be very tricky to them. The right table shows the effectiveness of our proposed countermeasure. For both the primary and the mirror, their false acceptance rate surges a lot and the adversarial impersonation attack. For example, the mirror one jumps from around 6% to 63%. With our proposed, the FA actually reduced, and the last, which is the strongest attack, the ensemble MAFGSM attack. Our proposed can also be combined with existing countermeasures. For example, since we are using the robustness gap between models for detection, adversarial training can be adopted to strengthen the mirror model. This could result in more significant score inconsistency. Finally, the last question is that when the countermeasure will fail. This approach fails when the score inconsistency vanishes under attack. For example, the attacker gives equal force to push the non-target trails towards the top right corner. This could be possible when the threat model, which is a model used to craft attack interpretations, does not come from any of the two models, the primary and the mirror. And in such a case, we find that combining adversarial training could be a good option. This is beyond scope of our paper, but we made such an experiment. We use adversarial training to strengthen R vector's robustness, which is the R vector strong here. And we also use it to weaken R vector, which is the R vector weak. With the MAFGSM attack generated from X vector, which is an unseen threat model, we show that the non-targets are also separable in the 2D space. Due to time limited, we only highlight the main idea and the results in this presentation. You can read the paper if you are interested. And thank you for your time.